MFI zeolite is important in industrial practice in the areas of catalysis and adsorption separations. It can also be used in membrane constructs for separating molecules. MFI stands for Mobile 5. Mobile is the name of the corporation. They're responsible for the synthesis of MFI zeolite several decades ago. The Mobile Corporation is now a part of the Exxon Corporation. This is a unit cell of MFI zeolite. It consists of straight channels and zigzag channels. The channel dimensions are approximately 5.5 angstroms. Further structural details are provided in this table. These are the unit cell dimensions. This is the framework density, pore volume, and surface area. Let's get a feel for how molecules align along the straight and zigzag channels. Let's begin with normal hexane. Normal hexane has a length that is commensurate with the distance between two intersection points. So this is the distance between two intersection sites, and you can place a normal hexane precisely to occupy the distance between two intersection points. So it aligns along the straight channels and along the zigzag channels without any problem. The maximum loading that is achievable is 8 molecules per unit cell. These are the unary isotherms. And this is a computational snapshot of normal hexane at a loading of 4 molecules per unit cell. And approximately half the pore space has been occupied here. And at 8 molecules per unit cell, the entire pore space would be completely occupied. You will note from the data here, the green squares is a unary isotherm for 2-methylpentane, which is an isomer of normal hexane, and the maximum loading is just 4. Let's try and understand why it's 4 and not 8. 2-methylpentane needs more leg room than is available within the channels. So it prefers to locate at the intersection sites. This is the XY view, and the XZ view, which is from the top. You will see that only the intersection sites are occupied. And there are 4 intersection sites per unit cell, and that explains why the maximum loading is just 4. The same is true for adsorption of iso-butane. Iso-butane, because of legroom considerations, prefers to locate at the intersections. And you can locate them within the channels, but you need an extra push. Aromatics such as benzene and ethylbenzene also prefer to locate at the intersections because of the availability of more room, and therefore they are less constrained. This is ethylene or ethene. Ethene can locate easily within the straight channels and the zigzag channels, and indeed MFI zeolite is used in the catalytic process for ethylation of benzene to produce ethylbenzene, and the adsorption and diffusion characteristics of ethylene, benzene, and ethylbenzene of vital importance in the design of fixed bed reactors for acylation of benzene. Another point to note is that the mobility of ethylene will be severely reduced because of the location of aromatics at the intersection points. Using the analogy or metaphor of molecular traffic, we can examine the situation in a busy street in Pune in India, and the motion of motor cars and scooters, bicycles will be hindered by the slow moving elephant. And the quantification of the slowing down effect is of essential importance in the design of MFI catalyst or adsorbent in several practical applications. So in order to gain a quantitative insight into how the molecular traffic is impaired by the presence of slow-moving gas molecules, we performed MD simulations at a temperature of 300 degree Kelvin for a variety of mixtures, and the details of the MD simulation methodology and diffusivity data are available in these publications. Let's first look at a mixture of carbon dioxide and hydrogen. Hydrogen, being a very small molecule, has a high mobility, and it jumps very fast within the straight and zigzag channels. CO2 is much more strongly adsorbed and has a much lower mobility, and therefore the hydrogen molecules, even though they have a high mobility, the trajectory they can follow is severely restricted, because somewhere along their trajectory they will encounter a slow-moving CO2, and they cannot pass the strongly adsorbed CO2. To carry the metaphor a little further, let's consider MFI zeolite to be made up of a checkerboard with several adsorption sites. CO2 is strongly adsorbed at the sites indicated by the red circles. The blue circle represents the adsorbed hydrogen, and it has a high mobility, but the area it covers is just restricted to this contour. To go further beyond this contour, the CO2 molecule has to vacate vacate that site, but that occurs less frequently. So it is the diffusion of CO2 and hydrogen is analogous to a game of musical chairs. In order for hydrogen to occupy any chair, the CO2 has to vacate the chair, and CO2 has no inclination to vacate a chair easily or quickly because it's very strongly adsorbed. And these slowing down effects have a vital influence on mixture diffusion of CO2 and hydrogen. This is verified in experimental data of the permeance of hydrogen and permeance of CO2. If we look at the experimental data on unary permeation, we'll see hydrogen permeates much faster than CO2 because each component is on its own and there is no mutual interactions. So CO2 permeates about 1 order of magnitude more slowly than hydrogen. But the situation is completely reversed in the mixture. CO2 is more strongly adsorbed than hydrogen. It prevents hydrogen from diffusing because of the slowing down effect. And because of the slowing down effect, the permeance of CO2 is about 1 to 1.5 orders of magnitude higher than for permeance of CO2 is 1 to 1.5 orders of magnitude higher than for hydrogen. The same is true for permeation of CO2 and methane. Methane has a higher mobility, but in this case, it is unable to cross this intersection point because of the CO2 molecule, which even though they're moving about at that adsorption site, they have no inclination to vacate those adsorption sites quickly. See, mixture of methane and ethane. Methane has a higher mobility, but it's in the mixture with ethane, its mobility is severely reduced. This shows the animation for a mixture of methane and propane. The mobility of methane will be severely impaired due to the presence of propane. Let's look at separations of normal and branched alkanes. In this case, this is iso-butane. It's located only at the intersection points. In a mixture of normal and iso-butane, iso-butane will occupy the intersection points. The normal butane will may occupy anywhere along the channels. And if we look the animation, the normal butane, in this case colored red, will be unable to cross the intersections here. Look at this molecule. It's moving about, but it cannot cross this, it cannot cross that. These are data from PFG NMR of the self-diffusivity of normal butane with increased loading of iso-butane. As the number of molecules of iso-butane increases, the self-diffusivity of normal butane decreases significantly. Say at a loading of 2 molecules per unit cell, where half the intersection sites are occupied by iso-butane, the self-diffusivity is reduced by about 2 orders of magnitude. And at a loading of 4 molecules per unit cell of iso-butane, the entire traffic is brought to a complete standstill. Experimental data is provided in this article. Analogous situation holds for a mixture of a normal hexane that can locate anywhere along the straight channels or zigzag channels, and 2-methylpentane that locates only at the intersections. Because of the location of 2-methylpentane at the intersections, the normal hexane molecule will not be able to cross the intersection points. The red normal hexane is severely hindered in its motion due to the firmly ensconced 2-methylpentane at the intersection sites. Benzene undergoes rotations and also does an occasional somersault at the intersection points. There's a cyclohexane that also prefers to locate at the intersections, and even though it rotates freely, its motion along the channels is virtually non-existent. In other words, it diffuses very, very slowly from one intersection point to the other, and prefers to be located only at the intersections. This has implications for mixtures of alkanes and benzene, or alkanes and cyclohexane. Let's have a look at a mixture of benzene and methane. Methane has a higher mobility, but the path it follows is restricted due to the fact that the benzene molecule is blocking the intersection sites. This is experimental data on the self-diffusivity of methane with increased loading of benzene. The self-diffusivity of methane is reduced by about 2 orders of magnitude when the loading of benzene corresponds to 2 molecules per unit cell. So the traffic comes to a virtual standstill if more than 2 intersection sites are occupied. The understanding and quantification of such traffic junction effects is of vital importance in the design of fixed bed adsorbers and fixed bed reactors, such as reactors for ethylation of benzene to produce ethylbenzene.